So our first simulation is going to deal with Mountain Dew. It says that they have a special promotion in which they're giving away free prizes. Mountain Dew claims that under the caps of 1 in 6 bottles, there is a prize awarded. Mr. Wilcox purchased an 8-pack of Mountain Dews. None of them were winners. He thinks Mountain Dew is lying about their claim, and I apologize. That should just be a period, not a question mark. So, the imitation of chance behavior based on a model that accurately reflects the situation is called a simulation, and that is what we're going to be focusing on today. Now, you will start to notice that your homework, sometimes I write the homework problems, sometimes I steal them from textbooks, but you might begin to notice that they'll refer to something called the 4-step process. And when I write the questions, I will say use the 4-step process as well. The 4 steps to the process are state, plan, do, conclude. I always, when I think of the 4-step process, it makes me think of when we had to, and when I say we, I mean me, myself also, because when I went to school, we had to do work samples also, where you had to state what it was asking you. You did the math, you explained your math, you said this is my answer, and then you did a check. And this is what it reminds me of. We're going to state the question and that we want to answer, and we're going to put all the necessary information in there. We're going to plan what we're going to do, so we're going to write down our plan. We're going to do the plan, and then based on our do, we write our conclusion. So it kind of reminds me of those work sample type things. And really, it's just a way in statistics to remind you to think about what the question's asking, how is the best way to answer it, do that math, and then make your conclusion. And honestly, it's a great process that can be used in any math, but for whatever reason, we focus on it in statistics only, not in the other math classes. So, we're going to start by stating. So, we know that Mountain Dew says that 1 in 6 bottles are winners. Mr. Wilcox bought an 8-pack, and none of them are winners, so he thinks that they're lying. So we want to figure out what is the probability that we buy an 8-pack that has no winners when Mountain Dew claims 1 in 6 are winners. And I'm going to abbreviate Mountain because I'm lazy. So I gave the claim, I gave the situation, buying an 8-pack that has no winners, and we want to figure out what's the probability that that happens. So I gave it away. Our simulation is going to be using a die. So I have 3. But I'm only going to use 1. Last period I used green, so I'm gonna go with orange. It just looks so pretty under the doc cam. So my plan is to simulate the 1 in 6 winners by rolling the dice, because there are 6 different outcomes when I roll a dice. And I can choose one number to represent winning a prize, and the other 5 would mean that I don't get a prize. So my plan is to simulate by rolling a die. And I'm really bad about making sure I say die instead of dice when it's singular, so if I mess up, I'm sorry. But I'm not gonna correct myself, because that's too much work. So, anybody want to choose a number 1 through 6 that means we win a prize? Throw it in the chat, unmute yourself. Anybody want to pick a number? 1. Nate says 1. Well, Nate, you read my mind, because if nobody said anything, that's what I was going to say. 1 means we win the prize. Which means 2, 3, 4, 5, 6. 1.5 is not something I get when I roll the die, Nate. Gotta use something that's gonna show up when I roll my die. So 2, 3, 4, 5, and 6 mean no prize. So I have my 1 in 6 winners, the claim that Mountain Dew has. Then I need to define a repetition. So we want to simulate buying an 8-pack. So I'm going to say that 1 repetition is the same as 8 rolls of the die. And that will simulate an 8-pack. Now, anytime we do a simulation, we don't want to just do 1 repetition, because 1 repetition is not going to give us enough information. So we want to do more than 1 repetition. If you think about the definition of probability from last week, and I said that it's what happens in a very long series of repetitions, that is a good way to remember that you need to have more than 1 repetition. Unfortunately, when you're doing a physical simulation like rolling a die, you don't want to do so many repetitions that it takes forever. If we were using the graphing calculator and we could use random digit generator, we could actually do hundreds of simulations pretty quickly. But because we're rolling a die, we can't do a huge amount really quickly. So I'm going to go with 5 just because this lesson took quite a bit of time in the last period and I don't want to run out of time. 10 obviously would be better, but I don't want to do so many I run out of time. But I'm doing more than 1. Now, if you are using your own die, you're going to get possibly a different answer than me. Your repetitions probably are going to be different than mine. That's absolutely fine. That's what makes simulations interesting. So 5 repetitions. 1 repetition is 8 rolls. So I'm going to write it down because I can't remember. Trying to think about numbers and count to 8 to make sure I did 8 rolls is too confusing for my brain. So I'm gonna write down my 5 repetitions. And like I said, if you have a die, you can follow along, do your own die rolling, or you get to sit and watch me. If we were in class, I have tons of dice and we would all be rolling dice, and so much more fun than you guys just watching me roll a die. But doing what I can. So for my first repetition, 4 is my first number. Then I get 2, 4, 5, went off, sorry, it was a 1, is a 1, that's 5, so that's 6 rolls, that's 7, so I need 1 more in this repetition, so I have my 8 rolls for that repetition. Repetition 2, got a 2, a 1, got a 3, I got another 3, 2, 5, 1, that's 1, 2, 3, 4, 5, 6, 7, and last one's a 2. So that's repetition 2. 3, 2, that's 1, 2, 3, 4, 5, 6, 7. It was 4. So there's my first 3 repetitions. That's 5. That's 6. 7 and 8. So I've done my 4 repetitions. Ah. One, two, three, 4, 5, 6. And that's 1. All right, so I did my 5 repetitions. So a 1 means I got a prize in my 8-pack. So in this 8-pack, I have a 1, so I got a prize. In this 8-pack, I have 2 prizes. This 8-pack, 2 prizes. This 8-pack, 2 prizes. And that 8-pack, I also got 2 prizes. So we're going to make a conclusion. Now our conclusion is based on the simulation. So if somebody, did anybody else roll a die? Or did you all just watch me? All right. So if you had done it on your own, you might have gotten a repetition that had no 1s. You might have gotten 2 repetitions that had no 1s. So when you are doing a simulation, you need to say based on our simulation or based on my simulation, because my conclusion is only based on those 5 repetitions. So based on my simulation, I would expect to buy an 8-pack with no winners. Blank percent of the time. Now I left it blank on purpose. So for our 5 repetitions, my simulation, I had 0 8-packs out of 5 that had no winners. So that's 0%. So I would expect to buy an 8-pack with no winners 0% of the time, based on my simulation. Last period, when I did this, I had 1 8-pack that had no winners. So you can see I highlighted it. My 4th repetition had no winners. And honestly, I've used this example for probably 7 years. And I want to say every year I end up with 1 simulation or 1 repetition that has no winners. I feel like this is the first time I've always gotten a winner. So, so notice that 1 out of 5, 1 8-pack out of the 5 8-packs had no winners. So I said I would expect to buy an 8-pack with no winners 20% of the time. That's why the wording based on my simulation is so important, because it's just based on our simulation. We can't generalize it. We were able to test Mountain Dew's claim. If we were able to use graphing calculators, we could do a lot more than 5 repetitions, and our percent would be a better estimate. But like I said, when it's something you have to physically simulate, you can't do too many because then it's really time consuming. But you have to do more than 1, because otherwise it's not good enough. Any questions before I move on to our table of random digits? All right, so we're still working with the Mountain Dew simulation, but this time we're going to use the table of random digits, also known as Table D. In the homework, you may see it referred to as Table D. Now on this one, I got rid of the state. I just have the plan, do, conclude, because the state would be the same. We're still trying to figure out what's the probability we buy an 8-pack that has no winners when Mountain Dew claims 1 in 6 are winners. Now, a few things about this table of random digits. The first column is not included in the random digits. Notice up at the top it says line. So sometimes when they ask you to use a table of random digits, they're going to specify that you start on line 134. Okay? Sorry, I'm going to sneeze. Maybe. So they can tell you to start on line 101 all the way to line 150. The nice thing about the table of random digits is when they specify a certain line to start on, it ensures that everybody should get the same answer. Now, when you're looking at the table of random digits, they group them by 5s, because if it was just a string of numbers, it would get really confusing to read. If you're working with, let's say, 2-digit numbers, like something has a, I don't know, a 25% chance of happening, and you're reading 2-digit numbers, you would read 19, 22, and then even though the 3 is here and the 9 is there, you would read it as 39. So you do read it continuously. You don't like stop and ignore the 3 and read that as 95. You read it continuously. If you get to the end of a line and your simulation is not done, you just continue down to the next line. You can read single digits, you can read double digits, you can read triple digits. I suppose you could even do 4 digits, but I don't know. I've never asked kids to do a 4-digit one. I think that was it. Oh, the other thing, so you can see there's 9. If we're looking at them as single digits, 9 is the highest and 0 is the smallest. So it goes from 0 through 9. Every number is covered. So when we write our plan, we're going to say that we're using the table of random digits. I mean, it does say it, but in your plan, you should specify how you're doing your simulation. And then we have to specify what number is a winner, what numbers are not winners. I want to continue with this just for continuity. So I'm going to say that 1 means we get the prize. And 2, 3, 4, 5, and 6 mean no prize. Now, I just told you that the table of random digits goes from 0 to 9. We are going to ignore the numbers 7, 8, 9, and 0. And we have to specify that so that we can show that we are focusing on the numbers 1 through 6 with a prize having a 1 in 6 chance of winning. So even though you may think that saying this is enough, you do have to specify that if we get 7, 8, 9, or 0, we are going to ignore that number. The other important thing to notice here is that all the numbers I am reading are of the same length. They're all 1-digit numbers. Let's say if it said 1 in 10, and I was using the numbers 1 through 10, those are not all the same length, and so it would be hard to know. Let's say I was looking right here. Is that 1 after the 7, or is that 10 after the 7? So we have to be really careful in making sure our labels are all of the same length, which I'll talk about on the next page in the notes. But for now, 1 means win, 2 through 6 means no prize, 7 through 9 and 0 I'm going to ignore. And then just like before, we have to define what a repetition is. So 1 repetition means I'm going to get a list of 8 numbers to simulate buying an 8-pack. And again, I have to make sure that I do more than 1 repetition, but not so many repetitions that it's ridiculously time consuming. And like I told you before, I want to make sure I get through this lesson, so we're going to do 5. 10 would be better, but we're going to do 5. 100 would be better, but I can't do this 100 times. And again, I'm going to write it down, especially because I'm ignoring certain numbers. It's going to be easier for me to see if I actually write it down. So, anybody have a preference on which line number I use to start? you're gonna, oh, Piper said 123. Emma, you were right after her at 138, so I'm gonna go with Piper, sorry. So Piper wants us to start at 123. So in the do part, or the plan, sorry, I didn't put space between the words start and at. You do need to specify where you're starting. If, so some of the problems will tell you, start at this line. If they don't, you need to put what line you're starting at so that I could check your work. All right, so we're starting at line 123. So I have my paper under it, and like I said, I'm gonna write it down so that, because it's hard to keep track of, especially when you have numbers you're ignoring. So we have 54580. So the 8 and the 0 I'm ignoring, so I'm gonna write 545 down. And that's the first 3 in that repetition. Then I cross over. 8 I ignore, 1 I use, 5 I use, 0 I ignore, 7 I ignore. Then I come over here, 2 I use, 7 I ignore, 1 I use, 0 I ignore, and then 2 I use. And that finishes my first repetition. I have 8 numbers. So I finished repetition 1 right there. For repetition 2, I just keep going in the row. So 5 I use, 6 I use, 0 I ignore, 2 I use, 7 I ignore, and I go across. I use 5, and I use 5. I ignore 8, and I ignore 9. I use 2. Keep going. 3 and 3. And that finishes out that repetition. For repetition 3, I pick up where I left off. So that 0 is my first one, and we ignore zeros. 6 and 3. And then I'm going to come over here, 4 and 1. I ignore 8, and then I have 4 and 2. I ignore 8, and I have 1. And I ignore 8, and I have 6. And that is 8 for that repetition. Repetition 4 picks up where I left off. I ignore the 8, and then I'm at the end of that row. So I'm going to pick up at the beginning of line 124. I ignore 7, and then I get to use the 1. I ignore 0. I get to use 3 and 5. I ignore 0, 9, 0, and 0. I get to use the 1. 4, 3, 3, and 6, and then I ignore that 7. So there's repetition 4. And then I'm going to pick up where I left off for repetition 5. So 4, I ignore that 9. I get to use that 4, and I ignore 9 and 7. I ignore that 7, I get to use 2. I ignore that 7, and I get to use 1. I ignore the 9 and the 9, I get to use 6. I ignore 7, but use 5. I ignore the 8 and use 2. And that's 1, 2, 3, 7. Ignore the 7 and use the 6. And that finishes off repetition number 5. So when I make my conclusion this time, again, I want to make sure I say that it's based on my simulation, because for this simulation, the first 8-pack had 2 winners. The second 8-pack didn't have a winner at all. My third 8-pack had 2 winners. Fourth 8-pack also had 2 winners, and the fifth 8-pack had 1 winner. So when I write the conclusion, we need to make sure that we have those words based on my simulation, because our conclusion is only based on what we just did. So based on my simulation, I would expect to buy an 8-pack with no winners blank % of the time. And our simulation showed that 1 out of 5 8-packs had no winners, which is 20%. So based on our simulation, we would expect to buy an 8-pack with no winners 20% of the time. So when I rolled the die to do this simulation, it seemed like it might be that Mountain Dew was lying, because we got a winner in each repetition. This time, I got a repetition without a winner, so it seems like it is possible if we think about it as one big simulation. Out of the 10 repetitions, 1 of them didn't have a winner, so that would be 10%, right? So when it comes to simulations, the hardest part is usually the plan. Now, I'm sure some of you are thinking, wait a minute, the do was the hard part. The do may seem hard, but it's doable because we had a good plan. If we have a bad plan, it makes it impossible. And so making sure that we have a good plan is the most important thing, which makes it the hardest part, at least in my opinion. So on the next page of notes, we're going to focus on the plan. We're going to set up some plans using our table of random digits. We're not actually going to do the simulation. We're just going to set it up. And then at the bottom, we're going to read through some plans and see if they make sense or not. So like I told you, I have to remember where I told you. I don't remember where I told you, and I'm not going to try to point to something in that sea of notes. So when it comes to a plan, the most important thing when you're using table D, or that table of random digits, is to make sure that your numbers are all of equal length. Remember I said if we were using the numbers 1 through 10, sorry, my papers are falling. I said if we were using the numbers 1 through 10, it would be really hard to know, and of course now I can't find what I pointed to before, right here. After that 7, if we're using the numbers 1 through 10, is that a 1 or do I read it as a 10? So we have to make sure that when we set up our plan, all the numbers that we're reading are of equal length. So if we were using our table of random digits to pick random parts from a bin that contained 20% faulty parts, when I read 20%, percent means out of 100. So I automatically go to, okay, I need 20 out of 100 to be faulty. So I want to use the numbers 1 through 100 because that is percents. So 1 to 20 are going to mean faulty. And then 21 through 100 are going to mean not faulty or good. Now, like I said before, since they're not all equal length, it's really hard for me to know, do I read, if I was starting at the very top, do I read this as 1 or do I read it as 19? Do I read that as a 2 or do I read it as 22? Something like, I'm not going to find it in here, am I? Oh, right here. Do I read after the 9, do I read that as 1? Do I read that as 10? Or do I read it as 100? Since I don't have my numbers being all equal length, it's really hard to know how to read it. So when you do it, if you start like this is fine, but then you want to go, okay, my longest number is 3 digits. So I need to make everything else have 3 digits so that I know how to read the table and so that they all have the same chance of being read out of that table of random digits. So what we do is we put zeros in front of them. So 0 to 1 would be 21. 0 to 0 would be 20, and then 0, 0, 1 would be 1. Now they all have equal length, so I would know that when I got to that 100, I actually read it as 100. Now I personally want to read as short of numbers as possible, because trying to read 3 digits, keep track of things, that's, in my opinion, a lot of work. So there is a way that we can use 2-digit numbers here. We can go 00 to 99. 1 through 99 is 99 numbers, and then if I use 0, that would be the 100th number. But it would allow me to not have to have 3 digits. It would allow me to use 99 as my biggest number, and so I would only have to do 2-digit numbers. Now here's the issue with using 00. If I use 00 as my starting number, 19 would be 20 numbers. 1 through 19 is 19 numbers, and then 0 is my 20th number. And that's where I see kids make a lot of mistakes, is they write 00 through 20 because we're doing 20%. But when I do 0 through 20, that's actually 21 numbers. And so I just ruined my simulation because I have now made it 21% are faulty parts. So if you do use 0, be careful and make sure that you actually think through how many you are setting up for your simulation. So 00 through 19 are faulty, which means 20 through 99 are not faulty. And then because 20% is a pretty number, I can actually do this one out of single-digit numbers. So if I use 0 through 9, that's 10 single-digit numbers, and 20% of 10 is 2, so I would specify 2 of those numbers to mean faulty. So I would do 0 and 1 as faulty, And then 2, 3, 4, 5, 6, 7, 8, 9. I suppose I could have put 2 through 9 there. Sorry, not faulty. So see, there's so many different ways that you can set it up that the plan can be difficult. I personally try to get the length of my numbers to be as small as possible because it makes reading the table easier. However, I even make mistakes when I throw 0, 0 into it. So sometimes I prefer to do longer lengths of numbers just so I make sure I set it up correctly. But it's up to you guys. Any questions before I move on to number 2? All right, so number 2, still picking a random part from a bin. This time there's 23% faulty parts. So again, percent, my brain automatically goes out of 100. So I'm going to use my 3-digit numbers, 0, 0, 1 to 0, 23. Could be faulty, and then everything else would be good. 0, 24 to 100 are good parts. If you prefer, you can shorten it so that you only have 2-digit numbers. Just again, be careful about using 0, 0. 0, 0 to 22 would be faulty. And then 23 to 99 would be good parts. 23, if I try to use 10 numbers, 0 through 9, 23% of 10 is 2.3. So I can't use single-digit numbers with 23%. I can only use 3 or 2-digit numbers. Any questions on that one? No? All right, so the last one, still picking a random part from a bin. This time 20% are unfinished, 30% are faulty, and 50% are functioning. So 20, 30, and 50 are all pretty numbers, so we're going to be able to do out of 3 digits, 2 digits, and 1 digit. So I'm going to show you all of them just so that you see all the different ways, and hopefully one of them will click so that when you actually have to do this on your own, it makes sense to you and you're not just trying to randomly copy me. So I'm going to start with out of 100. So 20% are unfinished. So if I'm working with 100, I have to have 3 digits. So 0, 0, 1 to 0, 20 would be unfinished. The next 30% are faulty. So that would be 0, 21 to 0, 50. And then the last 50% are functioning. So that'd be 0, 51 to 100. And those are, I'm going to write good because functioning's a long word. So that's using 3-digit numbers. I can use 2 digits by using 0, 0. But again, I have to be careful. Everything's going to be bumped down 1. So 0, 0 to 19 would be the unfinished. And then 20 to 49 would be faulty. And then 50 to 99 would be those good parts. And then, like I said, before I started doing these, 20, 30, and 50 are all nice numbers, and I can apply them to 10. So I could even use single digits here. So 20%, remember up here in the first one, 20% was two numbers. So I would say 0 and 1 are unfinished. 30% of 10 is three numbers. So 2, 3, and 4 would be faulty. And then 50% of 10 is five numbers. So 5, 6, 7, 8, and 9. Those would be the good parts. Now, is this last one better than this one? No. They are both great plans. I just personally have a hard time reading three-digit numbers from the table. But if this makes sense, use that one. I'd much rather you did it out of 100 and made them all three-digit numbers than accidentally make a mistake by throwing 0 into the mix, okay? I don't know how many times I can tell you guys, I'm just lazy, and if I can find a shorter way to do something or write something, I'm gonna do it. I think all mathematicians are inherently lazy. They have like their own like language when it comes to writing. They have symbols that'll like replace long words, or like in like 3 or 4 words. Like this one means therefore. This means for every. This means contained in. This means suppose that. Like there's tons of little notations that mathematicians use because they're just too lazy to write out words. Remember back in geometry when you did proofs? My son's in geometry and they finished proofs, and he was asking me to help him study. He was like, Mom, can you help me with proofs? I was like, no, I can't. And he's like, why not? You know math. I'm like, tell me one of the like acronyms for a proof. He was like, AIT, AS. I'm like, yes, see, we only had SSS, SAS. Like, we didn't have all those IT, interior, IA, interior angles, ulterior. There's just too many of them. But mathematicians are lazy. We'll abbreviate things if we can. Sorry, I went off on a tangent there. So like I said, in your homework, sometimes you're going to have to set up how you would use Table D. You don't actually have to do the simulation. Sometimes you're going to be given a plan and you're going to have to determine if it is a good plan or not. So on these two, they already set up the plan. We're just going to say if it's good or not. So on A, it says, according to a recent survey, 50% of people aged 13 and older in the United States are addicted to email. To simulate choosing a random sample of 20 people in this population and seeing how many of them are addicted to email, use a deck of cards. Shuffle the deck well and then draw one card at a time. A red card means the person is addicted to email. A black card means he isn't. Calculate, that says continue. Continue until you have drawn 20 cards without replacement for the sample. So before we get into the plan part, without replacement, this is going to become something that we see a lot in our problems. It'll say without replacement or with replacement. What it means, in this case, without replacement, because we're working with cards, if I pull a card, without replacement means I leave it out of the deck and I continue with the deck without that card. So this means And like I said, you'll sometimes see with replacement. That would mean I draw a card, I put it back into the deck. I would have to shuffle in between each draw of a card so that it would get shuffled back in there so it could come up again. But so without replacement, I keep the card out. Now we want to simulate 50%. They say that a red card means addicted to email and a black card is not. Is that 50%? If I split a deck to red and black, is that 50%? I see Piper's beanie going like this. At first, yes. Oh, Nevaeh, I missed your comment. I'm sorry. And Nate says at first, yes. What do you mean, Nate?
Well, after you take out the first card without replacement, then it's no longer 50-50. There's a slight bias towards black afterwards.
So, do all of you know what's in a deck of cards? Before I get into what Nate was saying. Anybody, let's put it this way, no judgment. Anybody not know what is in a deck of cards? Because I will explain a deck of cards. And it's okay if I have to. All right. There are 52 cards in a deck. Total. We don't use jokers unless it specifies. But for probability, we tend to keep them out. So if they want you to think about jokers, it'll say with jokers. Of the 52 cards, 26 are red and 26 are black. There are 4 suits. There are hearts, which are red. There are diamonds, which are also red. Then there are spades, which, don't make fun of my spade. Spades are black. And clubs, which is like a 3-leaf clover, they are also black. So hearts, diamonds, spades, and clubs. Within each suit, you have ace through king. Ace being 1, and then you have 2, 3, 4, 5, 6, 7, 8, 9, 10, Jack, Queen, King. If it refers to face cards, those are the cards that actually have a face, that is only Jack, Queen, and King. Aces are not face cards. And I think that covers just about any type of question we would ask in probability. So back to what Nate was saying. So if the first card we draw is red, that had a probability of 26 out of 52. So that was 50%. So then the probability that I get red for my second card is 25 out of 51. Can't speak. I already took a red card out, so now there's only 25 of them. And I took a card out of the deck, so there's only 51 left. So notice it is no longer 50%. Now, even though it switches and it's not perfectly 50%, you have to think about if we were looking at the population of everybody aged 13 and older, and I know there are a lot more people than I'm going to use, but I'm going to use this number just to be for an example. Okay, let's say there's 100 people. Yes, I know there's way more than that for 13 and older, but let's say there's 100. So the probability that I pick Nate, if he's in this population, is 1 out of 100. I don't put him back into the population because I don't want to ask him my survey questions again. So, hold up. I want it to be 50%. Let's say that there's 50 girls, 50 boys. 50 girls, 50 boys. So, Nate is 1 out of 50. Okay, then the probability, no, he's 50 out of 100. Goodness gracious, my brain is not working. 50 out of 100. Then the probability that I choose Jad, I already chose Nate, so there's 1 less boy, and I am not putting Nate back into my population, so the probability I choose Jad is slightly under 50%. So it is a good plan in this case, because even though without replacement is going to change my probability here to not exactly 50%, the same happens with my population. So this one is a good plan. On B, it says a tennis player gets 95% of his second serves in play during practice, meaning the ball doesn't go out of bounds. To simulate the player hitting 5 second serves, we're going to look at pairs of digits going across a row in table D. If the number is between 00 and 94, the serve is in. If the number is between 95 and 99, the serve is out. So we want to simulate 95% of the serves staying in. They tell us that 00 to 94 means the serve is in. Now we have to think through that this is 95 numbers. 1 through 94 is 94 numbers, and then the fact that I include 00 makes it 95 numbers. And then I have to make sure that there are 5 numbers here so that it's out of 100, so that I actually have 100%. If I have 95 numbers here but only 3 numbers here, then it's 95 out of 98, and that isn't actually 95%. So then if I look at 95 to 99, meaning the serve went out of bounds, 95, 96, 97, 98, 99, that is 5 numbers. So I am looking at both of these being out of 100, which means that this is a 95% chance, just like we wanted to simulate, and this is a 5% chance, which is what we want. So this one is also a good plan. Are there any questions before I let you go?